This is 4-1 linear functions. In order for something to be a linear function, it needs to both be a function and be linear. So we're going to write out the definition and break that down for you. In order for a linear function to be a linear function, like I said, it has to be a function that is linear. That's actually the definition. I know that seems crazy, but we already know what a function is. A function has no double domain, or it passes the vertical line test. And in order for something to be linear, it has the word right in it, a line. It has to be a straight line. So let's look at these three examples and see if they are linear functions. So the first thing I'm looking at is if they are linear. I'm going to put a check mark next to linear or function. If they're both linear and function, then it's got to be linear function. So looking at linear, this is a straight line. So this one is linear. And for the function, it has to pass the vertical line test. So if I draw a vertical line anywhere down here, it can only hit at one point. So this passes the vertical line test, so it's also a function. So therefore, A is a linear function. B is not linear. It's not a straight line. It's a parabola. But it is a function. It passes the vertical line test. But it's still not a linear function because it's not both linear and a function. And C, it is linear because it's a straight line, and it is not a function because if you do the vertical line test, it hits at every single point. So this is not a linear function because it's not both linear and a function. When looking at a table of values, we already learned this in Chapter 3. This table of values is a function if there's no double domain. So I'm looking at the domain, the x values, and none of these repeat. So this is a function. And then to see if it's linear, you're looking at how much, if there's a constant change of both the x and the y. So in the x's, we're increasing by 1 every time. That's a constant change. And for the y's, we're decreasing by 3 every time. Well, that's a constant change. And so therefore, this is linear. Since it's linear and a function, it is a linear function. It may help to write down that if something's linear, when looking at a table of values, it would have a constant change in the x and y. So now looking at the second example here, I'll get my pointer out. This is a function because there's no double in the domain. And this is not linear because there's not a constant change in the y. There is a constant change in the x, but it has to be in both the x and the y. So it makes it not a linear function. When we were learning about graphs and graphing equations and functions, I might have given you something like y equals x plus 1, and when you graphed it, it became a straight line. But when we had something with x squared, we noticed that all of these formed parabolas, U-shapes. And then when we had absolute value of x, could have been x plus 1 or anything like that, anytime we had the absolute value, we ended up with a V shape. So there's some rules when I look at an equation. Right away, I know if it's linear or not. Really, it's going to be about y equals mx plus b, which we'll be learning in this chapter. But there's some times when something's not linear. And so if any time that the x and y is being multiplied together, like in the example here, that would make it not linear. Or if x has an exponent, like in the y equals x squared problem that we were talking about, that's not going to be linear. And if y is in the denominator is the bottom of a fraction, anytime y is in the denominator, it would not be linear. Other than that, they're going to be linear equations or functions.